Okay, ladies and gentlemen, welcome to Coach Hanik's graphical analysis review sheet. These are some of the questions that are on the review sheet with no answers. And then I have a couple questions at the end that are not on the review sheet. So it first says, describe in detail the motion of the object in the above graph. The first line we see is actually a curved line. And if you remember, on a displacement versus time graph, if you look at the circle, and we put a little roller coaster here, it's going down. We said that as it goes down, this kind of curve in quadrant 1 is acceleration, and in quadrant 4 is acceleration, and in quadrant 2 it's deceleration, and then deceleration in quadrant 3. So looking at the graph itself, I see that it has this kind of curve. Follow that, looks like this, so I know it's an acceleration. So this is an acceleration. All right, next part of the graph looks like this, and it is going to be a constant velocity. The line or curve on a displacement versus time graph represents velocity. Now in the first case it's a curved line, so it is increasing velocity. So an object that is increasing velocity, which is a correct statement, is the definition of acceleration. For the second segment here, where I wrote constant velocity, since the slope of the line is not changing, it has to be a constant velocity. On the next part is a horizontal line to the x-axis. And really what it means is that the displacement is not changing. If the displacement or distance, and if it was a distance versus time graph, is not changing, then it has to be at rest or not moving. And lastly, we have another curve that's going down. Well, this happens to be a constant velocity. All right. Now, what is the difference between all of these here? Well, I'm going to erase this. And we're going to look at this again. Since all of these are above the x-axis, we have to figure out what direction is. There's no line below the x-axis. So here, this acceleration is going in a positive direction. The next line is actually continuing to go in a positive direction. For the next one, since the object's at rest, it's not moving at all, so there's no direction associated with it. And then lastly, the other line is going to be in the negative direction. Now, we have already established in class that up is going to be positive, east is going to be negative, positive, south is going to be negative, and west is going to be negative. Or we could say up, north, whatever it may be, top of the page is going to be positive, right or east is going to be positive, west or left is going to be negative, down or south is going to be negative. So I have to look at all different ones here, and that's that question. So let's go to the next one. Okay, this one says, describe in detail the motion of the object in the above graph. This is a velocity versus time graph, so the first thing I know is the line or curve represents acceleration. So let's check this out. In the first one, we know that the velocity is increasing. If that is true, since it's going from 0 to some number, we don't know exactly what the numbers are, but it's increasing. If velocity is increasing, I know, since the slope of the line is going to be constant, that acceleration is constant. And I can tell that from the slope. Remember, A equals delta V over delta T. This is a velocity versus time graph, so it gives us the acceleration. So a constant slope, and I'll write this underneath here, gives us a constant acceleration. Ooh, sorry about that. All right, now we have a flat line. And this flat line is going to say, well, if I drew a dotted line here, it goes to some velocity. So this line has to be constant velocity, whatever the number is, and therefore acceleration equals 0 meters per second squared. Once again, the slope of the line is 0 if we would actually figure that out, so the velocity does change, does stay the same. The next section is just identical to this. The velocity is increasing, therefore it has a constant slope, which is the acceleration is going to be constant. The next line is just the same as up here. It has a constant velocity with no slope, so the acceleration is 0 meters per second. And now I'm going to erase this so we can see what's going on here. And I'm down to the last section here. And I know that, well, what does this line represent? So, for a velocity versus time graph, I know that above the x-axis is a positive direction, and below the x-axis is a negative direction. Different on a distance versus time graph. But for this one here, since it's still above the x-axis, I know it's going in a positive direction, and it's going to have the velocity is going to decrease, and the acceleration is going to be equal to negative some number, or deceleration in that positive direction. Well, once it reaches the bottom or the x-axis right here, I know that the velocity equals 0 meters per second. At that particular spot, it has no velocity, so it has no acceleration. But once it goes below the x-axis, now we have slightly different. Let me just erase some of this here. We have a slightly change. What happens is that it now went from an initial velocity of 0 to some final velocity that's greater than 0. And so what I could say now is that this thing in velocity increased, which means since the slope is constant, acceleration is a constant. We would have to find the slope of that. If you forget, the slope equation equals m equals delta y over delta x. Okay? And so it's a constant velocity in the negative direction. All right, let's go to the next question here. Hopefully there will be no more announcements. All right, base your answers to questions 37 and 38 on the graph below, which represents the motion of a car during a 6-second time interval. So looking at this here, number 37 says, what is the acceleration of the car at t equals 3 seconds? Oh, sorry, it says 5 seconds. I find my 5-second here, mark. Come down, I know that is 5 seconds, and that is a flat line. Well, I know on a velocity versus time graph that a flat line means v is a constant. It happens to be, if I draw a dotted line across, 10 meters per second. However, that's the velocity. Since it's a constant velocity, the acceleration has to equal 0 meters per second. Squared. You cannot have a constant velocity and have an acceleration at the same time. So I'm going to choose choice number 1, where it says 0 meters per second squared, because it's asking about the acceleration of the object and not the velocity. Number 38, what is the total distance traveled by the car during the 6-second interval? I'm going to erase all this so I can redraw on here. And I know that in 6 seconds, I'm right here. And to find the distance traveled, I'm going to find the area under the curve. So the first thing I'm going to do is break this up into two objects. And I'm going to find the area of a triangle, which is 1/2 base times height. And then for this one, I'm going to find the area of a rectangle equals base times height. So we have area of a rectangle, and it's 1/2. The base of that rectangle, I'm sorry, I apologize, of the triangle, not the rectangle. So area of a triangle equals 1/2 base times height. The area of the triangle equals 1/2, 4 seconds, which is my base, and the height is 10 meters per second. So we have here 20 meters for the area of the triangle. The next one here, kind of let the snake around here, says area of the rectangle equals the base, which is going to be 2 seconds. The height is going to be 10 meters per second. Doing that, I found that the area of the rectangle is 20 meters. I understand that my little box here looks like a square. It's really a rectangle. And I have 20 meters. Well, now I must combine these two for the area of the triangle plus the area of the rectangle to find that it is a total distance of 40 meters. And so I'm looking at my choices, and it looks like it's choice 3. That's 40 meters. All right, let's go to the next one. Question 42, a student throws a baseball vertically upward and then catches it. If vertically upward is considered to be a positive direction, which graph best represents the relationship between velocity and time for the baseball? Neglect friction. All right, so I have an object here that I'm going to throw up on a velocity versus time graph. First thing I do, I check all of them. They're all velocity versus time graphs. Sometimes they'll throw in distance versus time graphs. They don't want to be tricked up here, so we're going to find that. I'm going to get rid of that. So it's a velocity versus time graph. The first thing I know is when I throw an object up, it goes up to a certain height, so I have my initial velocity of some number. I'm going to make it up. Let's just say it's 10 meters per second. I don't know what it is in this particular graph. There's no numbers. However, I do know it's greater than 0, so it doesn't have to be 10. It could be 1. It could be any number greater than 0. It comes up, and the final velocity I know is 0. At that point, it stops and then changes direction and comes back down. Therefore, my initial velocity on the other side is 0 meters per second, and when it comes back down, it should be at negative 10 meters per second. Again, the negative represents direction, and remember, as the object goes up, gravity, which is equal to negative 9.81 meters per second squared, the negative represents direction, is always acting on it down. So as the object goes up, it slows down because of gravity, and then when it gets to the top, it accelerates down, negative representing the direction, in the same fashion of negative 9.81. Looking at that, I need to know I have initial velocity greater than 0. And then this object's going to slow down. It's going to slow down at a constant rate. Constant because this slope will equal g, or negative 9.81 meters per second squared, because that's what's actually slowing this object down. Slows it down so much that when it hits the x-axis, it actually goes to 0, which makes sense. And remember, on the velocity versus time graph, above it is the positive direction. Below it is a negative direction. Therefore, when it hits the x-axis, it is at rest. Vf equals 0. And on the bottom, you can look at it as Vi equals 0. And then, therefore, it accelerates at the same constant. And so if I was to find the slope here, I would hope that this would come out to negative 9.81, which would give me a picture of choice number 4. All right, hope that helps. Which 38, which graph best represents the motion of an object in equilibrium? This is really not for this this test, so I'll just quickly go over it. The answer happens to be number 3, and the reason why is because the acceleration equals 0. And when we talk about motion, we talk about forces, and we're just studying forces in this class, so I'm not really going to spend too much time. But if you have an equilibrium, or an object in equilibrium, the net force must equal 0 newtons. In order for that to happen, there are 2 choices. Choice 1, objects at rest. It means all the forces that are acting on an object, I'll give you an example. Here's a box on a table. All the forces vertically are canceling each other out. Horizontally, there's probably no forces if just the box is sitting on the table. Another way of looking at it is it has to be at constant velocity. If it's at constant velocity, that means A, acceleration, is equal to 0. If there's no acceleration, then and it's at a constant velocity, all the forces are balancing each other out, and therefore it would be an equilibrium. So we're going to skip that one. That would be on the next test. All right, here we go. Here are the bonus questions, I believe, that are not on the review packet. At what time after t equals 0 seconds does the object again pass through its initial position? So first thing I see is we have a velocity versus time graph. I'm going to start labeling this here. This is my positive direction. This is my negative direction. So I need to know where they actually meet or cross for this particular case. So first I'm going to do is find the area of this triangle. If I could find the distance here, because remember the area of the triangle will give me the displacement. And I really want to know where they actually equal each other. So if I could find the area of these two, so I do area of a triangle equals 1/2 base times height, oops, that's an h, and then we're going to do it twice. Area of a triangle equals 1/2 base times height. We might not have a tremendous amount of room on here, but we'll figure it out. So the area equals 1/2 base for the first thing is going first triangle is going to be 3 seconds. The height is going to be 20. That was going to be 20 meters per second. The next triangle is 1/2. The base is going to be 2 seconds this time, and the height is still 20. Oh, sorry about that. Meters per second. It's technology. Love it. All right. So I found that the first one, area of a triangle, is going to be here. 3 times 2 is 6, so it's 60.5. That's going to be 30. And then for the second triangle, I found it to be 20. So we have a half. This basically 2 cancel out this 2. We have 20 meters. Combine the two, and I know it's 50 meters. So I'm going to do this here. I'm going to erase up here, and I'm going to rewrite that this area is equal to 50 meters. Then, since I'm running out of room, I'm going to erase all this. And now I need to know at what point will the object, when it goes below the x-axis, actually equal 50 meters or greater, because it says it will pass through. So it's not actually trying to be at the same distance. So first I'm going to do the area of this triangle here. I need to know how many meters it actually moved in this triangle. And again, it's 1/2 base times height. The base was 2 seconds. Height is now negative 20 meters per second. Negative represents direction here, and I know that actually is going to give me negative 20 meters. So this section right here is negative 20 meters. Well, I need to know how to get to 50, so what I'm going to do is do the next one just over. I got to go slowly here because I don't want to go too much and then figure out what's going on. Let's find the area of that rectangle, which is base times height, and I know it's going to be 1 second, and the height 1 second, and the height was going to be 20 meters per second, which would give me an area of that rectangle to be 20 meters. I'm sorry, negative. I apologize. I missed that whole thing. Oh, that's not good. I always follow the negatives here. So I know that's negative 20. So negative 20 plus negative 20 gives me negative 40. I'm so close to 50. So I'm going to go one more. And I'm not going to do the math again because the math is all right here. And it says, it gives me another negative 20. So negative 20 meters plus negative 20 plus negative 20 meters again gives me negative 60 meters. Therefore, at this time right here, which is 9 seconds, is actually it will have surpassed what it did in this entire first part. So somewhere between 8 and 9 seconds, I don't know exact time, it will have reached 50 meters. And then at 9 seconds, it is passed already by 10 meters. So I'm going to have an answer of 9 seconds. It means that at 9 seconds, they will have reached each other and actually have passed. So the starting point. Let's look at the next one. So the displacement x of an object moving in one dimension is shown below as a function of time t. The acceleration of this object must be. First thing, this is an older question for us, for the regions. I'm going to remove the x and say that it's d. It's the same thing. People learn a different way, but we're going to put d in there. And then it's hard to see, but the t's right there. So we have a distance versus time. So I know on a distance versus time, if I look at it, it's the equations. Okay, what is going on here? Try this again. The average velocity equals distance over time. And so I know that if I have a distance over time, a sloped line like so gives me a constant velocity. So this line gives me a constant velocity. And so it says displacement on dimension, the acceleration. Well, since it's constant acceleration, a has to be equal to 0 meters per second squared. Since it's constantly increasing in speed, there is no acceleration. And this one's a very similar question. Again, I'm going to remove the x and just put d. This was the t again, if you can't really see it. So it says the displacement x of an object moving, or d, of an object moving in one dimension is shown above as a function of time. The velocity of this object must be. Well, we already talked about that just in the last slide. So this is a repeat, is that if it's d over t, this line must be a constant velocity. Looks like this is the last one here. The graph below represents the motion of an object traveling in a straight line as a function of time. What is the average speed of the object during the first 4 seconds? Well, I know it's the average speed, which is a v with a bar over it, equals d over t. D at 4 seconds is going to be 2 meters, and the time is going to be 4 seconds. And then that equals 0.5 meters per second. So I would write v equals 0.5 meters per second. And since there was no direction associated with this, I'm just going to say that's my answer. And that's it. Hope you enjoyed. If you liked it, please review it. Say yes, you liked it, or give me a comment. I'll post a comment, and I'll try to respond as soon as possible. Thank you.